Imagine a Formula One pit crew. A car screams into the box, tires are ripped off, new ones slapped on, and the car is just gone in under 3 seconds.
Right, it is incredibly fast.
Yeah, everything relies on absolute, uncompromising timing. I mean, if a single wheel gun engages like a fraction of a second late or the angle of the tire is just a millimeter off, the entire operation comes to a screeching, dangerous halt.
It really is a perfect comparison.
So imagine that high moving with enough kinetic energy to tear right through steel. Welcome to this deep dive into the high-stakes world of the automatic tool changer, or ATC, inside a modern tapping center.
And the precision required in that environment is just staggering. Our source material today is this highly detailed technical manual focused entirely on what happens when that perfectly choreographed machine suddenly stalls.
Yeah, and the mission for this deep dive is pretty clear. We are going to use this incredibly niche industrial scenario to really explore the mechanics of complex system synchronization.
Exactly. Along with, the physical dangers of reactive fixes and the actual science of preventative maintenance.
Okay, so let's unpack this. Because, my instinct when a machine stops working is just to hit the restart button, right? Like a frozen computer.
Well, absolutely. That is a very normal human reaction.
But according to the manual, when an ATC stalls, it is not a minor pause. Production stops instantly, alarms trigger all over the place, and the machine physically locks the entire tool change sequence down.
Yeah, and the risks are severe.
Yeah.
You are looking at tool jamming, wrong tool identification, and devastating damage to the spindle taper.
Not to mention massive safety hazards for the operator. So I have to ask, is this really a situation where a simple reboot won't work? What does this all mean for the operator on the floor?
Well, a simple reboot is actually the absolute worst action an operator can take in that scenario.
Wait, really? The worst?
Without a doubt.
Yeah.
You have to look at the physics of what just occurred. A tool change stall in a tapping center is not a software glitch.
Right, it is not a frozen screen on your laptop.
Exactly. It is a physical, mechanical lockup involving heavy parts moving at high velocity. The moment that stall happens, the fundamental synchronization is gone.
The synchronization between the mechanical cams, the pneumatic cylinders, and the electronic control systems, right? They just violently collapse.
Yes. So the machine physically cannot move without doing damage. It locks itself down as a critical self-preservation mechanism.
Oh.
The servo drives actually detect massive current spikes because something is physically preventing motion.
So if you bypass that lockdown and force a reboot to restart the cycle...
You're driving heavy metal components directly into each other. You're taking thousands of pounds of static pressure and forcing it through a misaligned mechanical path.
That sounds like a disaster. So if the machine violently locking up is the ultimate symptom of this desynchronization, what are the invisible forces pushing these systems out of rhythm in the first place?
That is the big question.
Because I look at these massive industrial machines and they seem completely indestructible. How does the manual trace this massive failure back to something as simple as mechanical wear?
Well, it comes down to the sheer volume of movement. High-speed daily changes cause inevitable wear on very specific, highly stressed components.
Like the magazine fork, the tool arm claw, the locating pin, and the tool pot.
Exactly. And the issue isn't that these hardened steel parts are snapping in half. The issue is that microscopic wear creates a tiny gap in the mechanical tolerances.
Right.
So when the gap between the fork and the tool holder expands beyond its tolerance limit, you get a leverage effect. The tool holder tilts slightly during the high-speed transfer.
Oh, that makes sense.
Yeah.
A tilt of even a fraction of a millimeter at the top of the holder translates to a significant angle at the cutting tip.
It effectively becomes a high-speed wedge driven straight into the mechanism.
Wow.
And beyond physical wear, you have the friction factor.
Yeah.
The physical arm of the ATC moves along guide rails and is driven by internal cams.
So if those paths lack lubrication, the physical arm encounters, like microscopic drag.
Right. It moves just a tiny bit slower than the computer expects.
Because the CNC system is timing this down to the millisecond, right? It expects the tool arm to complete its arc and trigger a proximity sensor in, let's say, 1.2 seconds.
Exactly. And if it takes 1.5 seconds because of dry guide rails, the PLC registers a fault and throws a timeout alarm.
The manual also highlights environmental contamination. The cutting process generates tiny chips.
That is a huge factor.
If one microscopic metal chip manages to seat itself between the tool holder and the tool pot, the holder sits proud. It doesn't lock into the exact geometric plane required.
And then the ATC grabs it, expects it to be at coordinate Z, but it's physically at Z plus zero point 0.2 millimeters.
And you have a massive mechanical bind.
Right. That macroscopic failure is entirely driven by microscopic variables. If friction slows the arm down, the mechanical sync is totally lost.
But what if the arm has no physical interference? Like the guide rails are perfectly lubricated and the arm simply lacks the physical force to pull the tool.
Well, that brings us right to the pneumatics.
Yeah.
Most tapping centers use an air over oil or a straight pneumatic cylinder to press down on the drawbar.
Right. To unclamp the tools from the spindle.
Exactly.
Yeah.
And the manual specifies that the ideal air pressure needs to be rock solid, typically between 0.5 to 0.7 megapascals.
Which is a lot of force.
It is. The physics behind that unclamping mechanism are intense. Inside the spindle, you have this stack of Belleville washers.
Those are the heavy-duty disc springs, right?
Yeah. And they are actively pulling the pull stud up to grip the tool securely.
Okay, so to release the tool, the pneumatic cylinder has to push down with enough force to completely compress that spring stack.
Yes, and release the retaining balls. But if your shop air pressure drops to, say, 0.4 megapascals.
Oh, the cylinder doesn't compress the springs fully.
Exactly. The spindle still has a mechanical grip on the pull stud.
And while the spindle is still holding onto the tool, the ATC manipulator arm just swings in and tries to rip it out anyway.
It is a violent mechanical tug of war. The manipulator arm is trying to execute the M6 tool change command, but the spindle hasn't fully released its grip.
So the components just tear into each other.
Right, and air pressure drops happen for several reasons. Air leaks in the plant, aging cylinder seals, or most commonly, moisture in the airlines.
Because water fundamentally changes the compressibility of the air in the pneumatic system.
Exactly. When the valve opens to push 0.7 megapascals of force, the water absorbs and disperses that kinetic energy.
Dampening the impact required to knock the tool loose.
Exactly.
So we have mechanical interference, we have a lack of pneumatic force. The third culprit the manual focuses on is electrical, specifically regarding spindle orientation or the M19 angle.
Yes, the M19 parameter.
I was trying to visualize this, and it's like trying to aggressively yank a house key out of a deadbolt when the key isn't perfectly straight up and down.
That is a great way to picture it.
If it's even slightly angled, it jams. And if you have a pneumatic arm trying to force that key out with hundreds of pounds of pressure, you aren't going to open the door. You're going to snap the key and destroy the lock.
Precisely. When the spindle stops rotating at 10,000 RPM, it has to stop at an exact specific angle.
Because there is a physical drive key on the spindle face that has to slide perfectly into a corresponding keyway on the manipulator arm.
Right. And this is dictated by a parameter in the servo drive, reading off an encoder.
So what happens if you experience parameter drift?
Well, perhaps the encoder's zero position shifts slightly due to thermal expansion in the spindle casting or mechanical slip. The M19 angle is compromised.
The spindle key hits the edge of the manipulator keyway instead of sliding into it.
The metal scrapes, the forces spike, the drive faults out on overcurrent, and the entire system stalls.
Knowing these three culprits, the mechanical gaps, the dampened air pressure from water lines, the drifting M19 parameter, the physics of the stall are really clear.
They are. But let's put ourselves back on the factory floor for a second.
Okay, the alarm is blaring, the line is down, the production manager is pacing. We know a forced recovery is dangerous, but the manual makes it clear that hitting reset isn't just bad practice.
It's catastrophic. A forced recovery on an ATC that has lost synchronization turns a recoverable fault into a completely catastrophic failure.
Wow. So if you clear the alarm and force the ATC motor to rotate...
Or if you manually actuate the pneumatic valves while the tool is still partially clamped in the spindle taper, you will bend the manipulator arm.
Ouch.
You will deform the magazine fork. And worst of all, you will score and destroy the spindle taper.
Meaning you're looking at a spindle rebuild that takes days and costs tens of thousands of dollars, all caused in a matter of seconds by hitting the reset button.
Exactly. The alternative is a very specific step-by-step diagnostic protocol.
Right. The manual introduces this golden rule: mechanical before electrical, static before dynamic.
Step 1 is achieving a safe stop. Do not blindly reset the CNC alarms. You leave the system locked in its faulted state.
And step 2 is visual inspection, accompanied by a critical physical safeguard: placing a block of wood or thick soft padding on the work table directly under the spindle.
Right. Because the moment you start troubleshooting and manually bleeding air valves, that pneumatic drawbar cylinder might actuate.
If it releases the pressure holding the pull stud, that heavy, sharp tool is going straight down onto the workpiece or the table.
And you must keep your hands completely out of the cam box and arm swing area.
Because if the pneumatic suddenly repressurize, that arm will violently snap back to its home position.
Exactly. Once the area is safe, step 3 is checking the mechanical paths for visible interference or chips.
Step 4 is verifying static pressures, right? The air and oil gauges.
Yes. Step 5 is verifying the dynamic signals. Checking the PLC diagnostics to see what the sensors are actually reporting to the computer.
And finally, step 6 is verifying the physical alignment, like the spindle orientation.
What's fascinating here is how this rigid diagnostic protocol is essentially engineered to manage human psychology.
How so?
Well, when the production line stops and the alarm sounds, the operator's biological response is stress and urgency.
Oh, definitely. Panic sets in.
The rule static before dynamic, mechanical before electrical, forces the human brain to override its panic response.
It forces the technician to slow down, break the machine down into fundamental physics, and observe the physical reality of the hardware before they are ever allowed to touch a digital control panel. But wait, I have to play devil's advocate here.
Go for it.
Time is quite literally money on a high-volume production floor, right? A down machine is burning cash by the minute.
Oh, absolutely.
Why take the time to go on a scavenger hunt, walking around the back of the machine, inspecting air pressure gauges and wiping down mechanical paths before just plugging in a diagnostic tool and checking the PLC screen to see what the error code says?
It's a fair question.
Isn't the computer drastically faster at diagnosing itself?
The problem is the computer only reports the symptom. It cannot diagnose the disease.
Right.
The PLC screen will flash a tool change timeout alarm. It knows the arm didn't reach the sensor in 1.2 seconds.
But it does not know that the guide rails are completely dry and the cam followers are binding.
Exactly. If you skip the mechanical inspection, check the PLC, clear the alarm, and force a cycle, the machine might limp through one more tool change.
But the physical friction is still there.
Yes.
Mm.
On the next cycle, the tool binds, the arm bends, and instead of taking 5 minutes to wipe down a rail and apply lithium grease, you are waiting 5 days for a replacement tool arm from the manufacturer.
You have to prove the physical world is sound before you trust the digital signals.
Precisely.
That distinction between treating the symptom and, treating the underlying disease is crucial. But ideally, we don't want to reach the point of an emergency lockup at all.
Right.
The manual insists that these machines provide extensive warning signs long before they experience a hard failure.
They really do.
Yeah.
An ATC failure is rarely a sudden event. The machine gives off auditory, physical, and systemic clues that the mechanical synchronization is drifting.
The auditory clues are the most visceral, I think. A healthy, cam-driven tool changer has a very distinct, stable, repeatable rhythm.
Like you could set a metronome to it.
Yeah, and the manual notes that you should be actively listening for abnormal metal friction.
Or sudden heavy impacts.
Scraping sounds, replacing that crisp rhythm.
Exactly. When you hear metal scraping or a heavy clunk during the arm swing, it means the physical tolerances are just gone.
The physical clues follow shortly after, right?
Yes. We discussed the visual cue of a slow tool arm, but tactile feedback is just as important.
Like if a maintenance tech is manually rotating the tool magazine and feels an inconsistent, heavy resistance at certain pockets.
Right. That means the bearings or the guide tracks are compromised.
What about tool wobble in the spindle? The manual calls this out as a major red flag during the change cycle.
Tool wobble indicates the taper alignment is failing during the transfer.
Okay.
When the manipulator arm inserts the tool holder into the spindle taper, it should be a perfectly concentric fit.
If the operator observes slight vertical movement, or if the tool flange is physically scraping the spindle face guard during insertion, the arm is out of alignment.
And if you ignore that wobble, every single tool change is slightly galling the inside of the spindle taper. Eventually, you lose your machining accuracy and you destroy the spindle.
Then you have the systemic clues. The needle on the main air pressure gauge jumping wildly or taking too long to recover during a tool change sequence.
Or the sound of hissing hoses near the pneumatic block.
Sensor lights on the I/O board flickering instead of holding a solid state. Or the most notorious warning sign. The machine intermittently failing an M6 command, timing out, and then working perfectly fine after the operator hits reset.
Yes, that one is a classic.
Ignoring intermittent M6 failures is exactly like ignoring a weird grinding noise when you press the brake pedal in your car.
That is a perfect analogy.
You can turn the radio up, ignore the sound, and the car still stops for a few weeks. until the day the brake pad material completely shears off and you are rear-ending a truck at a stoplight.
Intermittent faults are literally the machine begging for intervention.
Wow.
An intermittent fault is never a self-healing system. It is a loose encoder cable vibrating during heavy cuts. It is a proximity sensor whose detection range is failing.
Or it is parameter drift, where the machine occasionally misses its mark.
Right. When an operator hits reset on an intermittent M6 fault and it suddenly works, it's usually because the plant air pressure recovered just enough during that 30-second pause to unclamp the tool.
But the root cause, the water in the lines or the failing compressor, is still there, waiting to cause a hard crash.
Exactly.
So if the machine is giving us all these sensory clues, the heavy mechanical clunks, the visible taper wobble, the flickering I/O lights, the hissing pneumatics, translating that language into a proactive routine is the only way to prevent the crisis entirely.
It is.
Let's look at how the manual dictates proactive care in this high-speed environment.
The required paradigm shift here is moving away from calendar-based maintenance. You do not service an ATC once a month.
Right. Preventative maintenance in a tapping center must be strictly based on the sheer volume of tool changes.
Exactly. A machine executing 3,000 tool changes per shift experiences a fundamentally different physical reality than a machine executing 50 changes a shift.
It's counting cycles, not days. And the daily maintenance requirements are surprisingly manual. Clearing chips from the magazine pots, wiping oil sludge and airborne dust from the spindle taper.
The text specifically notes that a dirty taper directly causes that tool wobble we discussed, throwing off the geometric center line of the cut.
And you have to inspect the pull studs, the retention knobs at the top of the holder.
The pull studs endure immense stress. They're subjected to thousands of pounds of pull force thousands of times a day.
You are looking for fretting wear or metal fatigue on the knob, right?
Yes, because if a pull stud shears off during a cut, the tool drops out of the spindle at 10,000 RPM.
That sounds terrifying. Moving to the weekly requirements, you are managing the friction and the pneumatics, applying the correct grease to the cam followers and guide rails to prevent arm drag.
And crucially, purging the airlines.
Because water destroys pneumatic valves, you have to drain the water traps in the air system and verify that the regulator is holding that 0.5, 0.7 megapascal pressure under load, not just when the machine is sitting idle.
Exactly.
Here's where it gets really interesting to me. We are talking about a highly complex, multi-million-dollar industrial manufacturing process, turning out aerospace or automotive parts with sub-micron precision.
Right.
And the survival of that entire high-tech system relies heavily on a human being wiping off dust with a clean rag and draining a few drops of water out of a rubber hose.
It is pretty ironic.
All right.
But if we connect this to the bigger picture, preventative maintenance at this level is an exercise in rigorous data collection and environmental control.
It goes far beyond the janitorial tasks of oiling parts.
Exactly. The manual stresses keeping meticulous alarm records. You have to track the exact frequency of those intermittent faults to establish a mean time between failures for your specific components.
So you are stocking where parts forks, pneumatic seals, proximity sensors, long before they physically break.
Yes, you are tracking the data breadcrumbs so you can actively predict the future.
If proximity sensor X has flickered and caused an intermittent fault 3 times this week, you don't wait for the sensor to completely die and lock the machine up during a critical production run.
Right, you swap out the sensor on Friday afternoon during a planned maintenance window so the system runs flawlessly on Monday morning.
You are controlling the physical variables so the system can maintain its mechanical and electrical synchronization.
You respect the complexity of the engineering by giving the machine the exact physical environment it requires to function at high speed.
We started this deep dive with a catastrophic factory-halting machine lockup. A blaring alarm, a stalled automatic tool changer.
Heavy machinery violently colliding, the ultimate nightmare for a production line.
Exactly. And we trace that massive complex failure down to microscopic metal chips or tiny drops of water dampening air pressure.
Or even just friction from a lack of grease.
Right. We explored how the solution isn't a quick digital reboot, but a disciplined, step-by-step diagnostic philosophy. Mechanical before electrical, static before dynamic.
Proving the physical reality of the hardware before trusting the digital symptoms.
And finally, we looked at how listening to the machine's subtle warning signs allows us to build a cycle-based maintenance routine that keeps the whole F1 pit crew running smoothly.
The automatic tool changer is a masterclass in how rigid mechanical forces, fluid dynamics, and digital control systems must operate in absolute harmony. and how quickly that harmony degrades when we ignore the physical variables.
It really is. And it leaves me with this final thought for you to ponder. We've just seen how high-speed industrial machinery requires this incredible level of precise synchronization.
Yes.
It demands constant observation for subtle, easily ignored warning signs, a slight wobble, an intermittent fault, a change in rhythm. And it relies on meticulous proactive care rather than reactive forced resets to function optimally.
That is the big takeaway.
If a tapping center requires that much intentionality to avoid tearing itself apart, what does that tell us about the complex, high-speed human teams and organizations we work in every day? Are we actively listening to the subtle friction and the intermittent warning signs in our own environments? Or are we just ignoring the grinding noise, hitting reset, and waiting for an alarm to lock the entire system down before we finally pay attention? Something to think about. Thanks for joining us on this deep dive.